Welcome to today's Explainer. I am so thrilled you're here because we're jumping right into one of the absolute most powerful, foundational, and frankly life-saving tools in embedded C programming. We're talking about functions. If you've ever felt totally overwhelmed by massive walls of code, or kind of felt like you were just typing the exact same logic over and over again for your microcontroller, well, you're in exactly the right place. Today, we're going to break down what functions actually are, how they're structured, and why they are literally the backbone of clean, efficient, embedded systems. Let's get right into it.
Okay, picture this scenario for a second. You've got a task, right? Let's say you need to blink a simple LED in a very specific pattern, and you actually need that pattern to trigger at 50 different moments throughout your main program. If you're coding in a straight line, just top to bottom, linear and repetitive, you're going to be typing out those exact same 10 lines of pin manipulation, timing delays, and register writes 50 separate times. That sounds agonizing, right? Because it is. It completely turns your main file into a 10,000-line monster that is practically impossible to debug, not to mention it wastes massive amounts of memory on your microcontroller. It's an absolute programming nightmare.
So how do we fix this? Well, think about it like an industrial factory. That linear approach we just talked about, that's like building every single wheel on a car completely from scratch, by hand, every single time you need one. It takes forever. Instead, what if you just built a wheel-making machine? You build the machine once, you design it perfectly, test it thoroughly, and then whenever you need a wheel, bam, you just press a button. That is the exact mindset shift we need to make today to totally transform how you write C code.
Here's our roadmap for today's explainer. We'll quickly cover the code repetition problem, the robot factory metaphor, the anatomy of a C function, real-world embedded applications inside the CPU execution, and finally, recursion and what's next.
All right, part one, the code repetition problem.
So what is a function? Formally, it's a reusable block of code designed to perform a specific task, completely eliminating repetition. It's essentially a self-contained module. You give it a name, you pack it with your specific logic, like our LED blink sequence we talked about, and then you just tuck it away. From that point on, your main program doesn't actually need to know how the LED blinks, it just needs to know that it can ask the LED to blink. It is the absolute ultimate cure for that repetitive code problem.
Moving right along to part two, the robot factory metaphor.
This perfectly illustrates our ultimate goal. Don't build it by hand, just call the machine. You know, in programming terms, pressing that button in the factory is known as calling a function. When you call a function, you're temporarily pausing your main assembly line, letting this specialized little robot do its highly specific job, and then you're resuming your main line once it's completely finished. It's super clean, it's modular, and hey, if the machine breaks, you only have to fix it in one single place, not 50 different places.
Let's look at the syntax in part 3, anatomy of a C function.
So there are 3 mandatory pillars of C functions, and they map directly back to our factory. First up is the declaration. This is your blueprint. It's usually found way at the top of your file or in a header file, and it just tells the compiler, hey, this machine exists, here's its name, and here's what it looks like. Second, we've got the definition. This is where you actually build the machine. It's the physical block of code containing your logic. And finally, calling. This is physically pressing the button inside your main loop to actually trigger the execution. You gotta have all 3 for the whole shebang to work.
Now, we absolutely have to clear up one of the most notoriously confusing vocabulary pairings in all of programming: parameters versus arguments. Okay, think of parameters as the empty slots on the machine waiting for raw materials. When you design the function, you might say, hey, this machine requires 1 integer to operate. That requirement? That's the parameter. An argument, on the other hand, is the actual raw material you feed into the machine when you press the button. Actually, scratch that. Think of it like this. If you pass the number 5 into the function, 5 is the argument. Parameters are the empty slots, arguments are the actual data filling those slots. Make sense?
And of course, once the machine processes those arguments, it usually needs to give you something back, right? This is the return value. It's the finished product rolling right off the assembly line and handed directly back to your main program. Say you've got a function calculating temperature from an analog sensor. The return value is that final formatted temperature data. Now, not every function has to return something. We call those void functions. But when they do, return values are exactly how functions communicate their results back to the rest of the system.
Okay, part 4, real-world embedded applications. Let's bring this into the real world. In an embedded system, your microcontroller is juggling a crazy amount of things all at once. Motor control, LCD displays, UART serial connections, ADC readings, GPIO writes. I mean, if you wrote all of this linearly in one massive loop, it would be a completely unreadable catastrophe. So instead, we frame each and every one of these operations as a separate, isolated, modular function. You create an ADC read function, you create a UART send function, and then your main program basically just becomes this highly readable checklist of function calls, easily delegating tasks exactly when they're needed.
Let's dive under the hood for Part 5, inside the CPU execution.
Let's really slow down and trace this dynamic execution journey. Step 1, the CPU is just cruising along, executing your main loop line by line. But when it hits a function call, like blink LED, it literally has to drop everything and jump its program counter to a completely different part of memory where that specific function lives. That's step 2. But how does it know how to get back? Well, before it jumps, it leaves a breadcrumb. It saves something called the return address onto a special memory structure called the call stack. Step 3 is the function actually executing. And finally, step 4, when the function wraps up, the CPU checks that call stack, grabs that return address breadcrumb, and jumps back to the exact spot it left off in the main loop. It is this elegant, perfectly choreographed dance happening literally millions of times a second.
Finally, Part 6, recursion and what's next. So once you really master basic functions, you're eventually going to run into recursion. Recursion is simply when a function calls itself. Going back to our factory metaphor, this is a pretty wild scenario where the factory machine essentially presses its own button as part of its process. It's incredibly powerful for solving very specific mathematical problems or navigating complex data trees. But a quick warning for sure, in embedded systems where memory is super tight, we use this very carefully. Why? Because you want to avoid overloading that call stack we just talked about, which creates a literal stack overflow.
Which brings us to our final thought. We now know how to organize our code into functions, and we know the CPU is jumping all around in memory to execute them. But what if we wanted to directly access, pass around, and actively manipulate the exact memory locations where these functions and their data live? How do we give one machine the exact GPS coordinates to another machine's raw materials? Well, the answer is pointers. That is where the true, amazing, and slightly dangerous power of C programming really lies, and that is absolutely what you should be looking to learn next. Thanks for joining me on this explainer, and keep building cleaner, faster embedded code.